Hi, in a recent video, which I'll link in, where I explained all of the PCB manufacturing options that a typical manufacturer would give you when you go and check out and get your board manufactured. And I asked in that, would people like to see one on Flex PCBs? And a ton of people said yes. So a full-on Flex PCB video will have to follow this because it'll be quite in depth. But as it turns out, just yesterday we had a requirement come up for a Flex PCB adapter that we required for the new microsupply project. So I thought we'd just take a look at rather than just me do it and just send it away. I'll press record and we'll talk about the various options here. So this won't be an in-depth Flex PCB tutorial. This just happens to be a real-world thing that we need for the microsupply. If you want to see the microsupply, ta-da! Here it is. Doesn't it look sexy? Here we go. Oh, look at that. Microsupply. Ooh, beautiful. Thing of beauty. A joy forever. Doesn't have the LCD in there, but anyway. Yes, this actually really does exist, and we have it working. And as it turns out, we just got the USB power delivery circuit of it working the other day, and herein lies the problem. And this video will start out with a rant about ST, as in ST Semiconductor, because, well, we've had an issue with this. So let's take a look at it before we get to the Flex PCB. Well, bloody Altium designer. First time I'm using version 19 actually, and I get an object reference not set to instance of an object. I don't know. Whatever. Send it. Do I have to send and close? Can I just close? I don't want to send and close. Here we go. Anyway, this is the schematic for the USB portion of the isolated USB side of the microsupply. And yes, microsupply videos will come in due course. And what we've got over here is we've got an STM32F070F6P6TR microcontroller, because all those letters on the end matter. That's rant number one. The STM32F070 micro is very different depending on the letters you put on the end of it, and it's really freaking annoying. Anyway, so in the hardware prototypes that we've built, we chose this relatively low-cost STM32 micro because we're also using STM32 micro as the main micro on the isolated side as the main control element as well. And it's a little 20-pin TSOP package, and it's got 32K of flash. And we thought, oh, 32K of flash is plenty because we don't need to do much. All we need to do is some USB power delivery configuration type stuff, and of course USB comms, like serial type comms, HID interface stuff, and things like that. And it seemed at the time it seemed like a good choice. 32K was plenty. But as we've found out through great personal anguish, mostly on David's side, personal anguish of the development of this thing, USB PD libraries that come from the manufacturer are actually huge. They're enormous. And we actually chose a Richtech part down here. It's the RT1716, and that's the USB PD controller. So you can see these lines here, CC1 and CC2, they're control lines which go over to the USB-C connector here, over here, CC1, CC2, and they actually configure the USB power delivery specification. They negotiate how much power you can, the host can deliver and how much the load needs and all that sort of stuff. And we wanted to do it properly. By the way, when we chose this micro, as we'll look into, another ST micro that had USB power delivery built in was not available. The cheaper version of it wasn't available, as we'll see at the time of making that decision. And the one that did, I think, was grossly more expensive. So it was a cheaper solution to go for this 2-chip solution here. So the STM32, of course, has USB built in. Here it is here, USB. There it is. There's the twisted pair up there. And so it's got the USB controller, but the USB power delivery is handled via the I2C bus down here in this little tiny 8-pin RT17 Richtech RT1716. As it turns out, which we didn't know at the time, the Richtech library for USB power delivery is enormous. So is the ST micro one. The ST micro one is, I think it's like 2 megbits or something enormous like that. And the Richtech one was huge as well. And David's actually, and it wouldn't fit, neither of them would fit in the 32K of flash on our STM32 micro, let alone all the other stuff that we wanted to put in, the serial comms, the HID and regular USB stuff, and all sorts of stuff. Just the power delivery library was absolutely enormous. So David's had to work with the design engineers at Richtech to get the library down, and we've finally got it pruned down where we can actually fit the Richtech USB PD library into the 32K of flash on this ST micro that we're using. Unfortunately, we can't fit anything else, so we can't fit all our other stuff. And maybe if we keep working with them for longer, we might be able to get it down further where we can just squeeze everything in this 32K. But anyway, we've decided, bugger that, we're just going to put in a larger micro. And of course, Murphy's Law says that the package we chose, this 20-pin TSOP package, the largest part is a 32K part. So to get, say, a 128K part, we have to move to an entirely different package. And at this stage, we've got like half a dozen prototype boards built up. And they cost a fair bit to get these manufactured, and they're all working. So we don't want to just scrap those and have to rebuild boards from scratch. We're on a tight timeline at the moment, and we just want a little Flex adapter board that converts a TSOP package like this into a larger footprint for the larger part. Right, so here's a photo of the board here, and this is the offending chip right here that we have to convert. So what we need is a Flex PCB, because you can't really do this with a rigid. This is where a Flex PCB comes in real handy. What we need is some sort of Flex PCB which goes like this, up here like this, and goes down there like that. Please excuse the crudity of the model. Didn't have time to build it to scale or to paint it. There's our new chip, which is a quad flat pack, and then we will have pads on here like this with little via holes in them so that we can actually solder down to this board here, to the existing pad. So we remove this chip, we get our Flex PCB, which is very thin put the kettle on material, polyamide material, it'll be like a regular double-sided board, but it'll just be flexible so that we possibly fold it up or something like that. Although you can see that this connector's in the way here, so we could actually, do it something like this, perhaps. That might work. But then it's quite difficult because these are very thin. You've got to get down and solder it onto the pads down here. We might have to physically remove this capacitor here, but that's okay. That little tiny BGA there, that's that Richtech package. Isn't it a little pain in the ass? Anyway, it's cheap and it does USB USB power delivery negotiation stuff in it. So yeah, that's so we need some sort of Flex board. So at this stage, I'm thinking something like that. But the issue here is, okay, this is a real fine pitch. I think I'll have to double check. I think it's 0.5 millimeter pin pitch. So it's a real pain in the ass. So, really, if there's a couple of ways we can do it. Either to have little vias on the Flex like that, then you just put your iron on top of that and put your solder on, and then it just flows down through the vias and attaches to the pads underneath. And you could actually stagger your vias like this, perhaps. That's a common technique used on LCD ribbons and all sorts of commercial products like that. That just gives you a bit more clearance there to do those pads. So we could do that, or what we could actually do is have our Flex going like this through the pads like this, and then have little castellated pads on here, right? Little half moon castellated pads. And I've shown those on, I'll do it exaggerated here, okay? So imagine that's one little pad, and then you slice through them just like you would on a regular FR4 fiberglass PCB. You can do that on Flex as well, and then you could like sort of like just solder in like that. And then the board could actually be like this. If we didn't have room up the top here, like, because you know we've got this in the way, this is a large package, so the flex would have to flip up like that, and we could you know, it gets a bit messy, so we could have a flex shape like that, for example, and then all of your traces just run around here like this, and then you know our chip can just be flapped around in the breeze over here, no problems whatsoever, and then we don't need to fold the flex. But there's lots of things. This is what I'll go into in if I do a specific flex PCB, but I'll just touch on something like this. Like, you wouldn't do right angles like this on a flex. You round everything. On flexes, you round everything, including you wouldn't do your traditional right angle traces, like 45-degree traces like that. On flexes, you want to round your traces like that. So when it flexes, there's less, you know, mechanical stress on sharp junctions and stuff like that. So you want to just, you know, radii everything like that, just because it's nice for flex, because they flex, and you don't want sharp corners when things flex. All the mechanical engineers can tell you all about that. So even though this board that we're doing for this particular application won't actually flex, so to speak, it'll just sort of, you know, sit relatively flat like this on top of, you know, the existing chips and things like that. Just be careful if you've got exposed pads on the bottom, make sure they don't short out to the tops of any other components and things like that. So you'd have to put some sort of insulative layer on the back. So you can actually have another layer of poly put the kettle on material stuck on the bottom of your board so that none of your vias are exposed. And of course you could do tented vias and, you know, stuff like that. But just be careful that you don't, nothing shorts out. Because if you had a via that just happens to be here and it was an exposed one, and then that's sitting flush on this, on the top of this capacitor here, which is going to be larger than the physical height of the resistors there, oops, you can come a gutser and it's short, and it might be intermittent, and that'd really ruin your day. Murphy ensure that it'd be intermittent at the worst possible inconvenient time. Yeah, so I'm not actually sure how I'm going to run this one, whether or not I'll shape it. I think I'll put the chip, because there is, well, there's not room for it here, but here there's room for it before it gets to this planar transformer up the top here. So there's certainly room for the chip, because as we'll see in a minute, it's not a huge amount bigger than this one here, even though it's a quad flat pack. But, you know, as I said, it's got to like go on the top of this, and it's got to sort of bend upwards, and oh, I don't know, 6 of one, half a dozen of the other. Like, I haven't chosen yet. I'm about to lay this out and I haven't chosen which way to do it. Like, whether or not I go for like little holes here like this, whether or not I just go for little holes like this, little vias like that, staggered vias. That'll probably, and just have the board shaped like that. I think that'll probably do the business. Yeah, I'll just run with that, because then we can remove that capacitor, and we can either put it on top of the flex, or we can do some muntzing and physically take out the capacitor, because it's not, you know, it's not a big deal. It's just a bypass cap, and, well, you know, you can put it on the flex if you want. I could put a pad down for it, but yeah, it'll work. So anyway, that's the story behind what we're doing today. We're going to manufacture a flex manufacture, that's a new word. I'm going to run with that. We're going to manufacture a new flex PCB, just a mod PCB that literally has just the one chip on it plus a pad to solder down onto the top of this chip here. And you would design this like you would any other PCB. There's nothing special about Flex PCB design here, unless it does actually flex. And then, as I said, you want to use curved traces. By the way, bend radius of Flex PCBs, as a general rule of thumb, you want to keep the bend radius to 10 times, at minimum 10 times the thickness of the material. So if the material is, you know, 0.5 millimeter, the bend radius, you want at least 5 millimeters. That's just a rule of thumb. So I think with the pin pitch, we're probably going to have trouble with the castellations on here. I don't like our chances of getting castellations with 0.5 millimeter pin pitch on a flex. I've never actually tried it at that pitch before, so I don't know. I think the safer option is just to go for staggered via arrangements like that, and we'll just let the solder flow down through the vias like that. I think we'll give that a go. Right, so let's go over to the adapter schematic here, and what we've got is, we've just got the 2 chips. The new one is an STM-F070 again, but it's the CBT6 as opposed to the F6P6TR chip. God, TR, but you don't need the TR. TR is just tape and reel. That's just the package that it comes in. I've done a whole video on that, haven't I? I'm sure I have. Anyway, but this new chip has more pins, which we don't need, but it comes in a quad flat pack, hence why we need this little flex adapter board. But it's a functionally identical chip, except it's got 128K of flash. So let's actually, just for a rant, let's go look at the ST website. So and David he used to like ST, he was a bit of an ST fanboy, and then he started to greatly dislike them because they would announce all these chips without having like real proper support for them and stuff like that. And this STM32G0 series, which is a new one, as I said before, this wasn't out, this wasn't available when we originally chose the chip for the micro supply. The development's been quite some time, so it is a new one. Bloody modern websites. Look at this. USB PD. USB power delivery. The STM, the 32G, this is their new value series line, has USB PD in. So we could completely get rid of, well, a couple of bomb items here. Not only the rich tech chip, but also these resistors here for the pull-ups, a couple of caps here. We could consolidate our bomb, and it's cheaper. But it ain't that easy, because if you were just reading the top level here, you might think, oh, fantastic, USB PD. But let's go have a look at the data sheet, shall we? Well, you search in the data sheet for power delivery. You search for USB, and what? There's no mention of USB. Wah, 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 wah. Not only, if you actually go into the correct data sheet, not only does it say for the USB power delivery, it just says, oh, data coming soon or whatever. There is no USB controller inside this thing. So we've Kamagutsa right there. But if you're looking at sort of like the top level things like this, just trying to pick a micro at like first shot, you might say, oh, it's got USB PD, but it doesn't have an actual USB transceiver in it. So it's absolutely useless. So we can't use that value line series. What we have to go to, if you go, I'll save you the time of going through all the parametric searches and stuff like that. Well, you have to actually go to the G4 series down here before you can find one that has USB interface with power delivery, including the physical layer like that. And that one is about 3 times the cost of the dual chip solution with the rich tech power delivery controller and the F series micro that we're going to choose. So yeah, it's we've come a gutser there. Anyway, they've got a wanky video over here. I won't bother playing it, but it's how to create a USB power delivery sync in less than 10 minutes. And it goes through, and you got all the, it doesn't explain, well, does it explain? No, music. And it just, you know, it's using their cube software or whatever, and it's not explaining anything. It's just say, do all this, do all this, do all this, and you can implement a USB power delivery in 10 minutes. But it ain't that easy. But you have to actually, I think you have to contact them to get this library. You might even have to pay for it or something like that. I don't know. I don't want to know the details, but yeah, it just isn't this easy. They don't explain anything. So it's, anyway, that's their new cube software. Apparently, you know, they make it out to be, you know, you can just snap your fingers and you've got USB power delivery. No. Talk to David about this if you want. It is USB power delivery, implementing it correctly and thoroughly is a pretty horrific experience. Okay, so let's actually go down here. USB PD dead battery support. The content of this section will be provided later. Thanks a lot, ST. Like, yeah, you buy into these chips, they advertise them, you know, you might design it into your design, and then you go, if you didn't read this, you might go, well, how do I implement my USB PD? Yeah, do I follow some little YouTube tutorial video with all wanky music on top and that's it? Like, it's just, no. So yeah, ST. pain in the ass, but then a lot of manufacturers. Richtech hasn't been ideal, for example. The Richtech one is unfortunately not open source. Come on, Richtech, open source your USB PD. Anyway, we're trying to work with them so that all of our firmware and implementations will be open source, but I think we're going to have to rely upon some Richtech binary libraries, unfortunately. But they're trying to strip out all of the, we're working with them to strip out all the crap so that we can get a minimal implementation of USB PD that we need. So yeah, otherwise it's just, it's too big, and they've got undocumented registers, and we've had to get special spreadsheets from them which document these undocumented registers, and, well, to document these undocumented registers. There's a phrase. Anyway, which detail these registers that we didn't know anything about, because we found it in the software. They're accessing these registers that wasn't in the data sheets and app notes and things like that, and we had to ask them what's going on. And they do have the details, but yeah, they don't make them relatively public. So like a lot of manufacturers are like this. They just, oh man, the devil's always in the detail. Anyway, what are we, 30 minutes into the video already? Sorry. Anyway, we've got a PLCC chip, and we want to convert that to an STM32 like package over here. So we've got the adapter PCB. Now, here's where you can come a gutser real easy. So this is our chip, obviously the red, it's on the top layer there, as you can see, and then we've got a bottom layer down here. So we've only got a 2-layer PCB. Like I said, we won't do anything different to a regular, we wouldn't design this any different to a regular PCB. It's going to be exactly the same as you would lay out, except when you go to the checkout of the manufacturer's website, you'll choose Flex Pcb instead of this. Now, because this is 100% Flex PCB, it is not what's called a rigid Flex PCB, which I'll show you. This is an example of a rigid Flex PCB. It's like, I can't make these bend that I'm aware of. Anyway, you can see that these, they've got some caps, and presumably they're LEDs, right? So yeah, those caps and LEDs are on this Flex PCB section, and then you've got 2 other rigid boards, hence the name Flex Rigid, and that's got a battery on the bottom like that. I don't know what this board does, just an example which came with Altium. When I do my video, I might show a more complex example. But you can see how the Flex material, in this case, usually it's sandwiched in the middle. So if you've got a 4-layer board, for example, then your Flex material will be the 2 inner layers, and it extends into the PCB so that you can then fold the boards up like this and create all sorts of, you can make as many boards as you want, but you basically lay these out as one big PCB. Like, you've got multiple PCBs, but it's effectively done as one large board, including all the separate, you can have as many of these as you want. You can have 10 different rigid PCBs like this, all connected with all these Flex functionality. Do I have an example? Now here's an example of a traditional PCB that's connected with a flat Flex, and you can see the ribbon connector cable there and on the other end of the board over here, okay? And of course you need the connectors, and well, that's, you know, expensive extra BOM items, more things that can go wrong. Or you can integrate, oh sorry, I don't have the best example, we'll get a better example next time, but in this one here you can see that this PCB, if I flip it over, is actually flat Flex on the bottom of the PCB. It's not in the inner layer, as I said, but it's on the bottom, and then they've got this extra bit over here which then goes off to another board, so it's all integrated, so you don't need the connectors on there. And that's what they're doing here. You don't need any connectors because this Flex PCB here extends as a layer inside the PCB. Now, as I said, ordinarily you would wedge it, sandwich it in the middle, so it'd be the inner 2 layers of the PCB, because ordinarily I wouldn't recommend that you put it on the outside like this one, because it doesn't flex. There's more stress and the adhesion can come off and stuff like that. It is more rigid, no pun intended, I'm here all week, when it's sandwiched in the middle. But you can put it on the bottom like this, and the manufacturers will do whatever you want. But you can see that the bottom layers like that are the Flex PCB. And that is called a rigid Flex because it combines rigid FR4 PCBs with Flex. But in this particular case, we're not going to do this. We're just going to have Flex. And if you want to see how that works in the layer stack manager here, like here it is. Here's the bottom layer here. They've actually specified the bottom layer as poly put the kettle on, polyamide material. So the dielectric 1, dielectric 2s. So this is actually a 4-layer board, but it's got, so they could have put it in the middle, but they've actually sandwiched it and they've specified the polyamide on the bottom. Now this isn't the sort of data that would be automatically given to the PCB manufacturer. This is the sort of data that you could just specify in the Gerber. You could just say, you know, like instructions on the Gerber or instructions in an email or whatever. You can just say, right, my bottom layer is the polyamide material, so the flex on the bottom. Or if you wanted the flex on the top, you wouldn't actually have to change. So if we go into single layer mode here, you can see that that's the layer on the top layer. Then the middle layer is, there's no copper on the flex at all because there is no flex in the middle layer. It's only when you get to mid layer 2 or the one from the bottom that this one is flex. So you can see like the bottom layer is all flex, it's all ground plane. By the way, another recommendation is not to use solid ground planes like this on flex wherever possible. Usually you would cross hatch them. So you might put your plane out here like this, but then I'd start my crosshatch from inside here, and then all of this would be a crosshatch ground fill. And you might, if you tear down products, you might see that commonly is that they'll use a crosshatch ground fill, and that's for thermal and flex and stress reasons, which all the mechanical engineers can no doubt tell you about. But once again, that's another like rule of thumb. Unless you absolutely need a solid ground plane, you would do flexes as a crosshatch. But when it goes inside the board like this, you can certainly make it solid because it ain't flexing when it's sandwiched inside that fiberglass. And just here's some examples of rigid flex PCBs. So this one here, you can see that they've got the 2 copper layers in the middle. Then there's adhesive polyamide insulation with adhesive in there. There's another adhesive in there. Then you've got the FR4 pre-peg. So these are your rigid FR4s over here. And this is your flex material sandwiched in the middle. But as we're showing on the Altium example, we've got that flex on the bottom 2 layers. So this bit copper here and this copper here are manufactured as a flex. Then they manufacture the FR4 fiberglass ones separately, and then they'll stick those on the top. And it's generally nicer if you do it as a big panel like this, for example. That one's only got 2 separate boards, but you can see how they've designed those as a flex. And that one's got a little like a LCD connector or something, you know, some sort of ribbony thing at the bottom. So, and they've got some mouse bites on there. So that's, you know, that's quite a nice design. And there's just 2 boards with some flexes sandwiched, and then there's ones with multiple that might have it look, that looks like it's got like an RF connector on there or something like that. You know, more advanced ones like this, and you know, it can get really cool. But we're just going to manufacture a simple and solder directly onto a flex PCB. So you leave out the word rigid. So we're basically doing like a flex PCB like that. We're going to solder our components directly on to the polyamide material instead of fiberglass. It's the only difference. So from like a design point of view, it really is, if you're just doing flex, there's no difference. You just specify flex in your checkout. That's it. You might have to have a few design considerations for the mechanical flex part, but apart from that, the design process is exactly the same. So there you go. It's going to fold. This is the Altium design here. It's just going to like flex around like this. It folds up, and then so the 2 boards like that fold up like that, and then the flexi bits go around the outside into like a hockey puck configuration or something like that. And once again, this isn't really an extreme flex board. Like there's nothing really inherently, like 10 years ago, getting one of these manufactured, very specific. You had to find a manufacturer who was willing to do it. Now, it's practically a shopping cart checkout at some manufacturers anyway. Basically, all you got to do is tell them in your layer stack up on your Gerbers or wherever you tell them which layers are polyamide flex material and which layers are fiberglass material, and they'll just do it. Easy peasy. They'll just choose the material and get the job done. And of course, and then when they sandwich them all together, all of the vias from the flex layers will automatically line up with and be bonded to the vias on the rigid PCBs, but from a PCB manufacturer's point of view, the construction is exactly the same as a multi-layer PCB. And they don't care that you're using a flex material instead of a rigid material. There might be a few little process, things in there, but basically they don't care whether or not they're making an 8-layer rigid board or whether they're making an 8-layer rigid flex combination. It's just that one of the inner layers is made out of polyamide instead of fiberglass. Meh. Anyway, I'm getting way too much into that. So now, here's where you can come a gutser. As I said, right, you got to be very careful here. Now, this is, of course, all your PCB designs are always done looking through the board. So this is the top layer. By definition, it's the top layer, so it's the red layer here. Okay, so this is pin 1 over here. Now, ordinarily, this one, pin 1's in the correct configuration for the chip. But you'll notice it's blue, it's on the bottom. So this one's actually been flipped twice. Not only is the component being flipped from the top side, the red side, over to the blue side, but then it's been mirror imaged like that because we have to connect down to another board underneath which has this particular pin configuration. So if you didn't realize that, you could completely come a gutser and get your footprint back to front. So anyway, we're just going to have a chippy on there. Haven't defined the board outline yet, but yes, we're going to have a pad. This won't be a chip. This will just be some vias. So what we need to do now is go in here. Geez, look at that expansion on those pads. That's a bit how you're doing. That's touching. Look, there's no solder mask slither. If we go into 3D view, look at this. Look at this. There's no solder mask. No solder mask between pads there. I could easily bridge your solder out. So our solder mask expansion is too big. So we're going to have to change that. Solder mask expansion, 4 mil. So we'll change that. So that's coming from the rules. We could have changed the rules, but who cares? Doesn't matter. We're not worried about this. There we go. 1 thou solder mask expansion. That'll do it. So now, if we go in here like this, bloody error markers. There we go. We've got solder mask between our pads now. It's a Christmas miracle. So we can flip that over and you can see there's a chippy there. But of course there won't be a chippy because that will just have pads. Anyway, what we want now is we just want to go in and just put some manual vias. So let's do a pad that's, 0.3 millimeter hole, for example. That's all, because you want the solder to be able to flow through. You don't want it to be too small that the manufacturer is going to charge you more, for example. And then our pad is 0.5 millimeters. Here we go. There we go. Go to metric. So I do metric for hole sizes and for dimensions and boards and stuff like that. But for trace and space, I still like to do imperial. Sue me. Now it's going to give a clearance constraint there because I haven't set up the rules. I haven't done like anything. We could actually put 2 vias here. There's no reason why we couldn't have 2 like that, just in case like one doesn't make adequate connection. There you go. Those holes look enormous, don't they? But they're 0.3 millimeters. We could do, as I said, you could do one that's staggered, but I think that's, but then again, you've got to also get your soldering iron. You've got to have enough exposed copper on there to get your soldering iron on. So then you can heat up the pad and heat up the via that it goes through. And then the bottom of the bottom side of this, if you're flippity-doo-dah, the bottom side of this has to then transfer the heat also through to the pad which you're trying to solder to on the bottom of this on the micro supply board. So there's a bit of trickery required there. So I don't know. Should I go? People are screaming, use 1, Dave, use 2, go for the castellation ones. Now, of course, if I wanted to do the castellated holes, for example, I would just specify my board outline as going right through the center of those pads, and then they would manufacture it. They'd cut it, zoop, get the laser out, and whoop, straight through, and then I'd be left off with the castellated pads. But anyway, I think 2 like that will probably do the business. Let's get rid of those error markers. Now, of course, when we've just got the pads like this, of course, the soldering iron the only contact it's got is on the annulus ring around, that's called the annulus ring, the exposed copper around the via like that. So probably what you want to do, once again, you could do this as a slotted hole, for example. You could but no. Anyway, so what I'm just going to do is just put a fill. So what we can do is we can actually put a fill on the top like this, and of course this won't, we've got the fill there, there's a copper fill, okay, but the problem is we haven't removed the solder mask expansion, so we need to go to our solder mask, our top solder mask layer, and put in another fill like that, and bingo, we now have this nice big pad that we can get our nice chisel tip iron onto, and then the solder will flow down through these vias here, and of course we've got the matching pad on the bottom like that. So I think that's a good solution. And we'll just place that there. You'll notice how it takes up all the net names. All right, so this is looking pretty nifty. I haven't defined the board outline yet, but there you go. We've got our nice pads like that, and on the bottom side there, we've got our matching pads down there. We've got a solder mask between pads, so it should be all hunky-dory. Yes, I'm sure the anal retentives out there, Dave, pull back just a tad on those, on the annulus ring there. All right, so we'll just go via, how about 0.45? Will that do it? Oh yeah, good enough for Australia. In fact, it's bang on, is it? Ha, winner, winner, chicken dinner. So there you go. That is how, well, I've decided to implement. As I said, there's many ways to skin this cat. You could do castellated holes, you could do staggered vias and all sorts of stuff. You could do it as a slot. If I put my thinking cap on, I could probably come up with half a different dozen ways to do this. And now all we've got to do is route that, and we'll just define our board outline. Because as I said, I think we'll do it like that, I think, because otherwise you've got these resistors in the way. If you try and bend it up this side up here, you've got the resistors in the way, and you've got these, you know, and we can't take those out. So really, yeah, I think I'll just have it coming out like this, because there's a bit more gap between that Richtech chip and those pads than there is between these resistors and these pads down here. So, and then as I said, if you put the board and if you put the flex coming up here like this, then it's going to flip up on top of that. That's quite a large, thick package there, so it's really going to flip the chip up like this, and I don't really want that. So I think I'll have it coming out the side like that. Oh, hang on. Have I got pin 1 around the right way? No, pin 1's over here. I was going to come a gutser. Let's just double check on our micro supply board here. Yep. Pin number 1 is there. So I need to orient it. Of course, I had it oriented that way. Is that the correct way on the camera? Anyway, I think you know what I mean. If you've been playing along at home, then you know that I was going to come a gutser there. So yeah, need to double check stuff like that. So pin 1. So I want the flex to be coming out the bottom like this. So, because I don't think there's enough on the top. Yeah, I could know, because we've got the crystal over here. Could have it there. Ooh, I don't think the physical size of the chippy. I can just measure it, outline. But you got the switch as well, but we can put it off to one side. That's no problem. We're talking about 8.3 millimeters, 9.9 millimeters. So there you go. We don't have the physical distance. You know, always measure, don't assume. So even if we butted the pins right up against here, we do not have the room to fit in the chip in there. And likewise, we don't have, you can just tell, you can just physically, we're not going to have here. Okay, so let's allow for some flexy, because once you've got the chip on there, the chip's going to be like relatively, like the chip doesn't really bend. So this flex underneath this chip isn't going to bend. So we want to add, you know, some bend radius so we can just come up over that resistor, and then we can like put some insulating stuff on the bottom and then just stick it down with some, you know, elastic or some double-sided tape or something like that. You can just leave it flapping around in the breeze. Doesn't matter. It's just a prototype. This is not high-speed stuff. We do actually have a differential pair on here, and it's designated by these little differential pair markers because it is USB. So technically, we should route these as a... Well, you don't have to have controlled impedance, but if this was high-speed stuff, yes, you would look at controlled impedance, differential pair, length matching, alternate trace length matching these and stuff like that. But this, like, we're not transferring huge amounts of data. It's basically RS-232 type rates here, so we don't have to worry about. It's still route them as a pair just because you can and you should, but you don't have to worry about the nitty-gritty of that. Nah. So what we'll do is we'll just define an outline here. So we'll just put our little radii in there like that. We can just make this bigger to get all our traces out, of course. And we want our radii in there because that's the part that might flex, is going to flex a little bit. So yeah, you just want to take the edge off that. These corners, you don't have to worry about them. You can just keep them sharp. Doesn't really matter. Of course, that's showing up as like thick. I could go in there and physically set the three-dimensional thickness of that to the polyamide material to make it look a bit more realistic, but who cares? That will be our little board, but instead of being made out of fiberglass, it's going to be made out of poly put the kettle on. So I don't want this to be a routing tutorial, but here's where you move your chip around, use your rat's nest, and also rotate your component like this to see. You can see, oh look, these are all swapping over like this. This is probably not going to be pretty. So you can see that there's all these ones down here which have to get all the way over to here. Oh, I haven't switched. I'm still pad 1 over here. God, I'm dumb. What I'm going to have to do is take all of this and flippity-doo-dah that around. So like you can see all those rat's nests those nets are crossing over. So you know that's going to be ugly. These ones down here have to connect up with these ones over here. Those go over to the couple over here, go over to there, things like that. Right, so let's actually just place a trace here. Just willy-nilly, right? This is a 5 thou trace. You know, you don't want to go much smaller, but are you going to be able to get that through that pad? No, you're not. See, that's the problem, right? We're constrained. So really, we've probably got no option. We really don't have an option, really, unless you want to go to really fine tolerances. Why? Because you're just going to pay more. I'll just extend this all the way up to the top. Traces all up there, because there's nothing on the top side. Like, I don't care if that's all flapping, bending up or whatever. Doesn't really matter. I want to be able to get my damn traces out of there like that. All right, I do believe that is our finished design. I'm certainly not not going to write home to my mum about that one. Look, it's just slapped together. 5 thou traces, 0.3 millimeter holes. The vias aren't even tented, for example, so you might want to tent over those. But as you can see, that is the basic. I could pull back the width of that. And then we'll just solder our chip directly onto the flex, because you're soldering directly onto copper. Temperatures are a different, thing to FR4, not as tolerant, but no problems whatsoever. I don't know if I'll put the bypass cap on there or not, but anyway, that should do the business. All right, so that's our finished board, and we just generate our Gerbers exactly the same way as we would for a regular board. I've done videos on that. Let's just assume that we've generated our Gerbers, no problems whatsoever. Then you'd go over to your PCB manufacturer, then you'd choose FPC rigid in whatever shopping cart options they've got. You don't want rigid flex PCB, of course, because we're not manufacturing rigid flex. We're just manufacturing a flexible PCB. That tells them you want polyamide material, poly put the kettle on, instead of fiberglass FR4 PCB. We've got a 2-layer board. We just want single pieces. We don't want a panel. We don't care. You can get them to panelize it. They might panelize it for you, but no, I'm just happy with the little single pieces. So it's absolutely tiny. It's 22 by 12 millimeters, and like, we don't even need silkscreen on the thing. Let's just say we want 10 of these little puppies. FPC thickness, we can choose our thickness. Like, we want like 0.1, it looks like 0.1 is their standard, so that's fine. You don't want to deviate from that because that may increase your lead time and stuff like that, because you may not be able to share a panel with everyone else. Yes, they'll still do these flex things as a panel. A rigid flex would be very custom specific, so you'd almost certainly be buying your own panel there. And their minimum track space, actually 0.06 millimeters, that's like under 3 foul. That's pretty good. So we've got 5.5, so no problems whatsoever. Minimum hole size, 0.35. Oh, we've come a gutser. I should have checked this before I laid out my board. From this manufacturer anyway, it needs to be 0.35 millimeters. So yeah, they're just going to come back and reject that. So I can change into 0.35. How much are we looking at now? 5 to 6 days, quantity 10, $111. It's not particularly cheap, is it? What if we want 5? It's not going to matter, 5 or 10, because they're so tiny. They've got to manufacture this. Are they doing it just for us? No, like somebody else may not, like we may not be sharing a panel of flex material, for example, with them. E-test? No. Oh, it's a bit cheaper. There you go. Without the e-test, it's cheaper. We don't need the electrical test. I wouldn't bother. Seriously, I wouldn't bother with the electrical test for this. I'd just take my chances. So we get our silk screen for free. So, you know, might as well put a picture of a platypus on there or something. Meh. Now, there is some concern about this, is that, okay, our resistors, if we go look at our board over here, then we've got our resistors. These resistors are fairly close, okay? So we're going to have a bend in the flex going down like this. So you've got to flip it around. So we've got a bend like that, and then it's got to bend up over this little BGA down here is not, you know, it's not that high. It may not even be as high as the resistors. I don't know. It's a tiny little thing. But anyway, a bend line across there, right, just after that chip. So just the whole thing will try and flex up like that, for example, and then this chip overlays that. So you could argue that I probably should have put the chip down below the bend line of the top of that, and then you've got it bend in here, but I'm not really concerned about that. So you've got two intersecting bend lines like that. So maybe with hindsight, I should have put the chip down, the pins down around, like no higher than the other chip, because then the whole thing could flex along that axes like that, if you can see my cursor, if you know what I mean, if you know what I'm talking about. So yeah, I think it'd fit. I don't think it's going to be a problem. Once again, for production, you'd fuss over this sort of stuff. All right, just to avoid that dual bending radius, like intersecting bend radius at this point here, I might go with what I originally proposed. Might do an alternate one where I just route all the traces up around here, like half on the top, half on the bottom. They should be able to get around there. That's only 4.3 millimeters. Look, you know, you don't realize how small this is. And measure that from there over to this component over here. That's almost 7 millimeters. So, you know, the flex only comes to here. So we've got, you know, we can make it much, much longer. But as I said, because it's going to bend. It's going to bend along that pretty sharp, because those resistors are, you know, close to that chip. You could argue that, you know, there was heaps of room here. They shouldn't have been that close to begin with. But, you know, and we've already got those boards. So there's no point worrying about that now. And so then we don't have to remove the bypass cap there, for example. Yeah, it's not a very effective bypass cap anymore with the traces. Doesn't matter. Doesn't matter. She'll be right. No worries. And yeah, I think that will do it. So that will remove like this crinkle, you know, when you got two intersecting radii like that, because this has to bend at that point, this has to bend here, so this will all be crinkly cut, Smith's chips crinkly cut in here. So, and to avoid our Smith's crinkly cut, we will add a bend radius in here, because this is where it's all doing all the, I might even move this down a little bit down here, something like that. I'll just reroute that. Only take me 10 minutes. And because we can't get across there anymore, you might I might flip it. Actually, you could argue that, oh no, yeah, most of them are coming from here. I'm just going to leave it like that, I think. Maybe move the chip over here because, look, there's only 4 pads there that are connected. Oh, no, 6 over here, but a couple of those go over to there. So I might leave it, say, there-ish. That's working out nicely already. Look at that. I like that. I didn't even, like, trial that. It was just, like, yeah, just gut feel. Yeah, look at that. Bobby Dazzler. And I'm just going to be bang on the width of that, too. Just, like, guesstimating that. A winner. Oh, why can't they go to there? Now, you could argue that I can maybe increase the width of this, for example, because I had that available, and then route some extra traces around here like this from here. But really, when you look at this, I'm looking at this going, I don't know, these ones have to go over to here anyway. Then they're going to have that same routing squeeze constraint that I had through there before, and there's 3 of them, and I look, couldn't be bothered. I'll just route all these out on the bottom layer. By the way, sometimes when you're routing traces like this, often you will offset them. You may not have one trace above the other because there can be slight mechanical things there when you really get into tight bendies and things like that. So a technique which is sometimes used is to offset your traces like that, but for something like this, doesn't matter a rat's. Actually, I've come a gutser here a little bit, because, like, I can't obviously route them out in this direction, so I've routed these ones lowest point down here, because I might be able to snake one up there, perhaps, but, you know, it's nothing like sneaking one on the side. Look at that. So these ones will come around here like this, and, well, what do? You got to go all the way around here, all the way with LBJ, all the way right around here. So you got to, so it's Murphy will get you every time. The life of a PCB designer. No, that's actually the power ground. So there you go. Once again, like, you could leave it till later and then, you know, try and flood fill your way out of your routing problem, but, like, let me just get the other traces around and we'll see what's what. This is where I could actually go to the top layer, you know, power and ground here. You could argue that, okay, you could maybe route the top layer out like this and around, so, and push all those traces up. Yeah. You could argue that I could even move it one more like that, extend my board out. This is what you can do when your constraints aren't really, you know, major constraints. Now we've got a nice fat looking power trace coming around there now. Look at that. Wow. Did I already run that trace over there? Oh, there. Oh, from there to there, that's all. Okay, yeah, no wuckers. There we go, that's better. So we actually got a... Oh, got a nasty cross in there. So, yeah, we ran our 3.3 volt USB supply around there like that, and we can probably do a similar thing to our ground. And, of course, I could, you know, route multiple ones at the same time. Of course, I could select them and then bring them up all over and all that sort of jazz, but, yeah. And here's our differential pair. And as it turns out, we don't actually have to connect this on top because this would already be connected on our board. So there's absolutely no reason to connect those 2 pads there. But just in case this one doesn't make connection and this one does when you're soldering, just for completeness and for design rule checking, of course, you would then get this across here like this. No wuckers. There we go. Almost done. Just got to join up some grounds. There we go. We are done. We are fully routed. I didn't define I stretched my board outline just a tad there, so I'll redo that. But we are done. Look at that. There's our flex. Once again, I'll just tent those vias, but yeah, that looks neat. That looks like a winner chicken dinner. So we avoid that flex point in there. So, yep, I like that. Beauty. So there's not really much left to do there. I forgot to change those hole sizes. I will to 0.35 millimeters. And basically, all we need to do is add our shopping cart, upload the Gerbers, and Bob's your uncle. We should just get that flex board, because they shouldn't have any problems with that as long as you meet all the clearance guidelines, the hole guidelines, and stuff like that. And it's obvious in your Gerber what your board outline is on one of your mechanical layers. There's nothing fancy. We're not doing a fancy rigid flex and they need to know the layers stack up and all sorts of jazz like that. They'll just manufacture it as a 2-layer PCB. Pretty simple these days. When I was a boy, that was rocket science. Anyway, that's it. I hope you enjoyed that. I don't know how long this video's been. It's been quite lengthy, but if you enjoyed that, please give it a big thumbs up. And as always, you can discuss it down below. And we'll have to do a follow-up video when we actually get this and assemble it on the board and see if it works. It should. Fingers crossed. I don't know. It's a rush job. But it should. Can't see why not. I don't think we've come a guts or anywhere, but you never know. Never know your luck in the big city. So, anyway, hope you liked it. Catch you next time.